Hello and welcome to my science tutorials. In today's video, we want to look at dimensional analysis WASSCE physics past questions and answers. Before we begin, if you're new to the channel, make sure you subscribe to the channel and turn on the notification button so that you do not miss any of our latest video. So without further ado, let's begin. So we have example number 1. This is the SSCE 1999 question number 5. So which of the following dimensions is for kinetic energy? So the question is demanding we find a dimension for kinetic energy. So let's look at the solution to this problem. Solution. So kinetic energy is the energy possessed by a body by virtue of its motion. So it is given mathematically as half mv squared. So this is equal to, we still maintain our half. Okay, now the m is for mass, so we write mass, okay, multiplied by velocity square, multiplied by velocity square. Now velocity is distance over time. Okay, so distance over time is the velocity, so I now square it. So this is just the same as me writing mv squared. So I now bring my half here, then I put the dimension sign over here, so kinetic energy, okay, then I put it in this bracket, means the dimension of it. So this means the dimension of mass times distance over time. Okay, but the distance over time should be squared, the dimension of that squared. So this is equal to, so from here kinetic energy will be equal to half the mass, the dimension for mass will be m, just m, then multiplied by the dimension of distance, okay, is l, so we write l here. The dimension of time is t, so we put it like this because distance is measured in length, so the dimension is l, so we square it. So from here we have half m multiplied by, here will become l squared on t squared. Now if we bring t to the top, we'll have half multiplied by m, we have our l squared already here. When we send the time squared to the top, it becomes t minus 2. Okay, so ignoring the coefficient, the dimension for kinetic energy will be ml squared t negative square, and that means that our option A over here is the correct answer. So let's have a look at another example. Example number 2, we have to find the dimension of momentum, or the question is saying the dimensions of momentum are, this is SSCE 2002 question number 3. So let's look at the dimension for momentum. So solution. So momentum let me remove the dimension sign for now. Momentum is given mathematically as the product of mass and velocity. And so if we apply the dimension symbol, so it means the dimension of momentum will be equal to the dimension of mass multiplied by the dimension of velocity, okay, which in this case will be what? Distance on time. So this will be equal to, the dimension of mass is m multiplied by the dimension of distance is l divided by the dimension of time is t. So this will be equal to m multiplied by l. The t, if we bring it to the top, it becomes t raised to the power negative 1. The dimension over here for momentum will be m lt minus 1. And if we look through the possible answers, option C is the correct answer. So therefore, the dimension of momentum is mlt raised to the power negative 1. All right, let's have a look at another example. Example number 3. It said, which of the following is a derived unit of work? This is the WASSCE 2007 question number 1. Right, so let's have a look at how we can use dimension or dimensional analysis to find the unit of work. So let's write down our solution. So work can be defined as the product of force multiplied by distance. So if you move an object with a particular force over some distance, the product of the force and the distance becomes the work. Now, let me break this down. This can be equal to, so work represented by W will be equal to, the force is equal to mass multiplied by acceleration. We use acceleration here, acceleration, then multiplied by distance. Now, take note that the acceleration over here and the mass gives you the force over here. So this is equal to, so the dimension of work will be equal to the dimension of mass multiplied by the dimension of acceleration due to gravity. So acceleration multiplied by the dimension for distance. Now, mass will give me m. Acceleration, okay, that will be velocity square. Sorry, acceleration is velocity over time, right? The rate of change in velocity. So that will be velocity over time. Okay, so let me still put this over here. Multiplied by distance. The distance is L. That's the dimension of distance. So if you look at it, velocity, okay, as we saw in the previous example, velocity is distance over time. So the distance is measured in L and then the time is in T. So the dimension for velocity is LT minus 1. So if you look at that, or we use that in place of the V over here, we'll have mass here multiplied by, then here the top will become LT minus 1 over T multiplied by L again. So from here, let me continue down here. I have M multiplied by here the LT minus 1 over T. If we send the T to the top, it also becomes minus 1. So we'll have LT minus 2 then multiplied by L. So from here, we know that the dimension for work will be equal to M. The L will multiply each other. We'll have L squared and then T minus squared. Okay, so this is the dimension. But how do we derive the unit from this? So we know that the M stands for mass, okay? And mass is measured in what? Kilograms. So we have kilograms over here. We know L stands for distance, okay? Now the distance is measured in meters. So we have meters squared. And then we have T over here. T, which is time, is measured in seconds. So we have seconds raised to the power minus 2. So this becomes the unit for work. Okay, so from here, if we look through the possible answers, we can see that option D is kilogram meter square per second square. Okay, so that becomes the correct answer for this particular example. So thank you so much for watching. This is how we use dimensional analysis to solve how to derive the unit of a particular work. And these are some few examples of practical questions that came in WASSCE. So thank you once again for watching, and I'll see you in the next video. Bye bye. Hello and welcome to my science tutorials. This is the part 2 of the dimensional analysis WASSCE phases past question and answers. So without further ado, let's start with this example that we have. So the question says, which of the following dimensions is that of force? And this is the WASSCE June 2011 question number 1, or WASSCE June 2011 question number 1. All right, so let's have a look at the solution for this problem. So we write down our solution. Now they say, which of the following dimensions is that of force? So force can be given to us mathematically as the product of mass times acceleration. Now you know that acceleration is velocity over time, or the time rate of change in velocity. So therefore it means when we are finding the dimension for force, that will be equal to the dimension of mass multiplied by the dimension of velocity on the dimension of time. Okay, and this will be equal to the dimension for force will be equal to the dimension of mass is m multiplied by the dimension of velocity. We know that velocity is distance over time, okay, and that will give us lt minus 1. So the dimension for velocity is lt minus 1. If you watch the previous part 1 of this tutorial, you realize that velocity is distance over time, and then the distance is measured, or the dimension for distance is L, then the time is t, so it becomes lt minus 1. So here you have t at the bottom. This t here is the time over here at the bottom that we see over here. So this is equal to the mass multiplied by the lt minus 1 at the top. When we send the t at the bottom to the top, it becomes lt minus 1 again. So we have the mass multiplied by lt, here becomes minus 2. And so if we join them together, we have mlt minus 2 as the dimension for force. Okay, so our correct answer over here in this particular example is the option B, which gives us mlt minus 2. Alright, so let's have a look at another example. Example number 2. It says what the dimension of power is. Okay, so we have been given the options, and this is the WASSCE June 2009 question number 3. They are asking for the dimension of power. Okay, so let's look at that. Solution. So power is equal to work done over the time taken or just time. So if we break down work done, we know that work is equal to force times distance. The work done in moving an object is the product of the force over the distance, and then this is over time. Okay, now to save us time, I apply the dimension over here. Okay, in the previous example we saw the dimension for force, so I will not go through again. So I will just apply the dimension over here at once. But if you don't know, you break it down like I did in the previous example, and then you get your dimensions. But I won't do that since we just saw the dimension for force. So I just apply the dimension for all of them over here, and so this is what I will get. So from here it means the dimension of power is equal to that of force we saw in the previous example is mlt minus 2 multiplied by distance, which is also L, on time, which is t. So if I look here, I have L here, so it becomes L squared. So I have ml squared t minus 2 on t. So if I send this t to the top, I have ml squared t minus 2 minus 1. This t comes to the top, it becomes minus 1. So our final answer for power, the dimension of power, will be ml squared t minus 3. So if you look through the examples, we see that option 3 gives us that answer. So our correct answer for this particular example is option C. Alright, so let's have a look at one final example for this particular tutorial. So the dimension of work are, we have option A, ml squared t minus 2, B, mlt minus 1, C, mt raised to the power minus 2, and then D, ml raised to the power minus 2, t raised to the power minus 2. This is the WASSCE November 2009 question number 1. Alright, so let's have a look at the solution to this problem. So the dimensions for work, okay, we already saw this, but let me do this again. So for work, okay, or work done, we know work is equal to force multiplied by distance. And then again, I know that force is mass times acceleration multiplied by distance. Okay, and then again, if you know that of acceleration, which is LT minus 2, you can proceed from here. If you don't, you can still further break it down as mass. Then acceleration is what? Velocity over time. Then multiplied by distance. Now, as at this point, you should know that the velocity, the dimension for velocity is LT minus 1. So you should be able to apply it straight ahead from here. So I will not break it further down. I'll just continue from here and apply the dimension to all of them. It means the dimension of mass multiplied by the dimension of velocity on the dimension of time, then multiplied by the dimension of distance. Okay, so this will be equal to the dimension of work will be equal to m for mass multiplied by LT minus 1 for velocity, then on time multiplied by the distance, which is also another L. So I have here, if I send the t at the bottom to the top, it becomes minus 1. So I have here m multiplied by LT minus 2 because I send the t at the bottom to the top multiplied by another L. So finally I have here m, the L, I have 2L here, power 1 plus 1. Then the t here will have minus 2. So my final answer is ml squared t minus 2. So this becomes the dimension for work. So if we look at that, we see that option 1 gives us that answer. So the dimension for work is ml squared t minus 2. So option A is the right answer. So thank you so much for watching the part 2 of this particular WASSCE physics past questions and answer on dimensional analysis. So thank you once again, and I'll see you in the next video. Bye bye. Hello and welcome to my science tutorials. This is the part 3 of the dimensional analysis WASSCE past questions and answers. So without further delay, let's begin. So we have question number 1. The dimensions of moment of inertia are, and this is the options that we have. We have ml minus 2, b ml minus 1, c ml, and d ml raised to the power 2. And this is the WASSCE June 2013 question number 3. Alright, so let's have a look at the solution to this problem. So solution. Now, dimensional analysis involves the fact that the student has to know the formula for most of the quantities that we use in physics. So if you don't know the formula, you are going to be found wanting. So I suggest that you memorize as many formulas as possible. Alright, so inertia is given to us mathematically as mass multiplied by radius square. Okay, square. So the formula actually for inertia, let me use I, will be equal to mr squared. Okay, but I'm just writing it just because we are doing dimensional analysis. So the dimension of inertia will be equal to the dimension of mass multiplied by the dimension of radius, okay, which is a type of length, squared. So the dimension of mass is m multiplied by the dimension of L. Radius is L, it's just like length. So we have L squared. So our final answer here will be equal to ml squared. This becomes our answer for moment of inertia. So if you look at it, option D gives us that correct answer. Alright, let's have a look at another example. They said the dimensions of the gravitational constant G are, and then we have the options over here. This is the WASSCE June 2012 question number 1. Right now, if you don't know the gravitational constant, okay, now the force of attraction between two bodies, okay, is directly proportional to the mass of the two bodies and inversely proportional to the radius between the two centers of these two bodies. Okay, so let's look at the solution to this problem. So the gravitational constant, we can get it from, let me write down the solution. We can get the gravitational constant from the fact that force between two heavenly bodies is proportional to, okay, so let me use the proportionality sign. It's proportional to the product between the two masses and then the radius between them squared. Now, if we remove the proportionality sign and we introduce a constant, that constant is g, which is the gravitational constant that we are asked to find the dimension for. So in this case, all we have to do is to make g the subject. If we do that, if we make gravitational constant the subject, we will have g is equal to F, which is force, multiplied by radius square, which is r square. I'm just going to leave it like that, over the product of the two masses that we have over here. So if I apply my dimensional analysis to them, I'll have the dimension for force multiplied by the dimension for radius squared over the dimension of two masses, so mass 1 multiplied by mass 2. Okay, so from here we know, okay, from all our previous example, that the dimension for force is ml minus 2, mlt minus 2, multiplied by radius is in length, okay, so we have L with the square over here attached to it. Then we have two masses, it will be m squared over here. So from here we can do some cancellation. One of the m will cancel one of the m's over here. We'll be left with 1. So we'll have the 2l over here. We'll have l1 plus 2. Okay, they have the same base, so we add the exponent. Then t minus 2, and then we have m at the bottom. So if you look at it, our final answer is going to be, the top here will have l cubed t minus 2 on m, and this is equal to, if we bring m to the top, it will become m minus 1, l raised to the power 3, t raised to the power minus 2. This becomes the dimension for the gravitational constant. And if we look through our answers, we can see that option, let me see, option C gives us that answer, and so option C is the correct answer for this particular problem. All right, let's have a look at one final example. They said, which of the following dimensions represent impulse? Okay, so let's continue and have a look at that particular example. By the way, this is the WASSCE June 2017 question number 2. Right, so let's have a look at the solution. So impulse in physics is equal to the product of force and time. Okay, so if I apply the dimension over here, the dimension of impulse will be equal to the dimension of force, which we already know because we've seen it already, so there's no need to go through it again. Okay, we said that force is mass times acceleration, okay, and then mass is m, acceleration is lt minus 2, and so the dimension for force is mlt minus 2, then multiplied by the dimension of time is t. So from here we have m l t minus 2 plus 1 from here, and so our final answer will be m l t minus 1. So this will become our final answer, and so option B over here is the correct answer for this particular example. So thank you so much for watching. These are some few objective questions on dimensional analysis that came from SSC time to WASSCE time. And thank you so much for watching once again, and I will see you in the next video. Bye bye.